Welcome to Civil Engineering Edge. In today's video, we're going deep literally into the fascinating world of underground metro construction. Imagine tunnels beneath bustling cities, seamlessly moving millions of people, supported by a maze of engineering marvels. From designing safe tunnels to managing utilities, this video is your one-stop guide for understanding the step-by-step process of building a metro below the ground. We'll explore everything: planning, excavation, ventilation, power systems, signaling, and more. Stay with us till the end for expert insights and real-world examples that will make you appreciate the metro train you're riding on. 1. Project planning and feasibility. Every great engineering marvel begins with an idea, but that idea must be feasible, financially sound, and technically viable. Let's understand how underground metro projects begin their journey. Key elements of project planning: demand forecasting. Engineers analyze current and future transport needs using population data, city growth projections, and travel behavior. This helps determine where a metro is needed and how many passengers it must serve. Route identification. Planners identify corridors with high traffic congestion or limited surface transport. They choose underground alignments in dense urban areas to avoid land acquisition issues. Technical feasibility, soil conditions, groundwater levels, nearby structures, and seismic zones are studied through geological surveys and borehole data. This determines the technical viability of tunneling. Environmental impact assessment (EIA). Potential impact on the environment, such as noise, vibrations, emissions, and disturbance to water bodies, is evaluated. Measures for mitigation are suggested. Financial feasibility. Cost estimation includes land acquisition, construction, tunneling, systems installation, and maintenance. Funding sources include central, state governments, multilateral banks, for example, JICA, World Bank, or public-private partnerships. Wrap up 4. Section. Project planning is the invisible backbone of every successful metro. Without meticulous research, no amount of engineering can bring an underground metro to life. 2. Route design and geometric alignment. Once planning confirms the project's viability, engineers begin drawing the invisible tracks on the city's blueprint. This is where design meets precision route geometry. Key aspects: horizontal alignment determines the metro line's path in plan view. Sharp curves are avoided for comfort and speed. A minimum curve radius is maintained depending on train type. Vertical alignment. Elevation changes are calculated to avoid utility clashes, maintain gradients not exceeding 3.5%, and enable natural water drainage. Tunnel depth. Deeper tunnels avoid surface disruptions and utilities but increase cost. Shallow tunnels ease access but face more utility conflicts. Station location design, position based on passenger access, intermodal transfers, land availability, and emergency access. Geometric design tools. CAD software, 3D BIM models, and route optimization tools are used for designing horizontal and vertical curves with accuracy. Wrap up for section. Designing a route underground is like solving a giant 3D puzzle under a living, breathing city where space is tight and precision is everything. 3. Tunnel design and boring methods. Now we enter the heart of underground construction tunneling. Building strong, stable, and safe tunnels is one of the most technically demanding parts of a metro project. Types of tunneling methods. 1. Tunnel boring machine (TBM). Giant machines with rotating cutter heads. N. Suitable for long tunnels under dense cities. N. Offers safety and speed while minimizing surface disruption. 2. New Austrian tunneling method and ATM. Rock support using sprayed concrete and rock bolts. N. Adapted in variable geology. NI requires expert monitoring during excavation. 3. Cut and cover method. Digging from the surface and covering the tunnel after construction. N. Economical but disruptive. N. Common for shallow-depth tunnels and station boxes. Tunnel lining and waterproofing precast segments. T-beam is install precast concrete segments to line the tunnel walls. Gaskets and waterproof membranes prevent groundwater ingress and ensure long-term durability. Ventilation shafts and emergency cross passages allow air circulation and provide safe evacuation routes during emergencies. Wrap up for section. Tunneling is like surgery beneath the Earth's skin. One mistake can impact the city above. That's why engineering precision and safety protocols rule the underground. 4. Station box construction and entry, exit access. A metro is more than just tunnels. Stations are the gateways. They connect the underground world to the city above. Station box construction. 1. Excavation. Earth is removed using controlled blasting or mechanical diggers. And temporary retaining walls, diaphragm. Slurry walls prevent soil collapse. 2. Base slab and walls. Waterproof concrete slabs and RCC walls form the box. And expansion joints and chemical waterproofing ensure leak proofing. 3. Mezzanine and platform levels. Levels are constructed for concourse, ticketing, and boarding. N. Escalators, lifts, and staircases are embedded in structural design. 4. Entry, exit access. Head houses are built at street level. N. Designed to connect with bus stops, auto stands, or other metro lines. Utilities and passenger facilities. Toilets, lighting, fire detection, signage, platform screen doors, etc. Wrap up for section. Station construction isn't just about concrete, it's about creating accessible, safe, and efficient spaces where engineering meets human movement. 5. Track laying and alignment. With tunnels complete and stations rising, it's time to lay the foundation for smooth and safe metro rides. Literally. Track laying and alignment is a precision-driven stage that forms the core of any metro operation. Types of track structures. 1. Ballasted track. Traditional system using crushed stone ballast. N. Rare in metros due to maintenance and space issues. 2. Ballastless slab track. Reinforced concrete slabs with direct rail fixation. N. High durability, low maintenance, better alignment control. Track laying process. Survey and benchmarks. Laser-based total stations maintain precision. N. Base preparation, concrete slabs with embedded rail seats. N. Rail positioning and welding. Rails are flash butt or thermite welded. N. Alignment checks. Done for leveling, curvature, cross level. N. Noise and vibration control. Floating slabs and elastomeric pads reduce noise. Narrator wrap up for section. Track laying might seem like a simple task, but it's a meticulous process of science, surveying, and safety. Every millimeter matters. Point 6. Power supply and electrification systems. A metro system without power is like a body without a heartbeat. Powering an underground metro is a complex yet finely tuned system that ensures trains operate smoothly, safely, and efficiently. Let's explore how electricity keeps metros on the move. Metro power requirements. An underground metro requires power for traction movement of trains, station lighting and operations, escalators and lifts, ventilation and air conditioning, signaling and communication systems. Types of electrification systems. 1. Third rail DC system, typically 750 volts DC. A power rail runs alongside the track. Compact and suitable for tunnels. Safer in confined spaces due to lower voltage. 2. Overhead catenary system, typically 25 kilovolts AC. Used in deeper tunnels or sections with more headroom. Requires overhead wires and pantographs on trains. Common in newer metro systems or high-speed sections. Power supply architecture. Receiving substations are SS. Draw power from the national grid, often 130 to kilovolts or 220 kilovolts. Step it down to usable levels, for example, 33 kilovolts or 25 kilovolts. Traction substations, TSS. Convert high voltage AC to DC for third rail systems. Located every few kilometers to maintain voltage stability. Auxiliary substations, S. Supply power to non-traction utilities, lighting, PVC, escalators, etc. Distribution system. High voltage cables run through dedicated cable ducts in tunnels and stations. SCADA supervisory control and data acquisition systems remotely monitor and control power flow. Grounding and earthing systems, crucial for safety and equipment protection, includes protective earthing pay. Return conductor systems. Stray current protection to prevent damage to nearby structures. Battery backup and UPS. Ensures uninterrupted power supply to critical systems like signaling, tunnel lighting, emergency communication. Stations and OCCs are equipped with diesel generators as backup during blackouts. Safety features: insulated conductor rails, automatic circuit breakers and overload protection, fire retardant cable insulation, energy efficiency measures. Regenerative braking converts kinetic energy during braking back into electrical energy. LED lighting in stations and tunnels. Smart energy management systems. Wrap up for section. Behind every moving metro is an intricate web of electrification systems working silently. From powering trains to keeping stations alive, electrification is the unsung hero of underground infrastructure. 7. Signaling and train control systems 1530 to set behind them. Narrator. Behind the seamless movement of metro trains and the safety of millions lies a sophisticated communication network, the signaling and train control systems. These systems are the nervous system of an underground metro, ensuring that trains run at optimal speeds, maintain safe distances, and react promptly to any anomalies. Let's delve into the technology that keeps the metro safe and efficient. Modern signaling systems. At the heart of metro operation is the modern signaling system, which relies on real-time data exchange between trains and centralized control centers. One of the most advanced and widely used systems is the communication-based train control CBTC system. CBTC provides continuous communication using wireless data links, allowing for accurate monitoring of train positions, speeds, and spacing. This results in optimized headways, improved punctuality, and higher capacity compared to traditional signaling systems. Key functions of a CBTC system include real-time train positioning. Trains are equipped with transponders and GPS-like sensors that constantly relay their exact positions to a centralized control system. This allows the system to calculate the precise distance between trains and adjust speeds accordingly. Adaptive speed control. The system can dynamically adjust train speeds in response to varying conditions, such as platform crowding or track maintenance. In emergencies, it can trigger auto braking or reduce speeds to prevent collisions. Automatic train operation ATA. Many modern metro systems integrate ATO with CBTC. Under ATO, the trains are operated semi-automatically or fully automatically, reducing human errors and ensuring smoother acceleration and braking profiles. Interlockings and safety verification. Interlocking systems ensure that track routes are set correctly before a train passes through a junction, preventing conflicting movements. Simultaneously, safety verification protocols continuously check system integrity, ensuring that any faults trigger immediate remedial action. Fixed block versus moving block systems. Traditional systems operated on fixed blocks, where the track is divided into segments. A train can only move into a new block if it is completely clear. However, modern moving block systems, as used in CBTC, allow trains to run with much shorter intervals since safe separation is calculated in real time, thus maximizing line capacity and flexibility. Levels of redundancy and fail-safe design. Safety in metro signaling is paramount. Systems are designed with multiple layers of redundancy. Redundant communication channels. In the event of a failure in one channel, backup channels ensure continuous data flow. Fail-safe principles. If the system detects an anomaly or loss of communication, it automatically initiates safe protocols such as halting trains or reducing speeds. Routine diagnostics and self-testing. The control system is equipped with self-diagnostic tools that continuously monitor performance. Any discrepancies are flagged immediately for maintenance intervention, reducing the risk of unforeseen incidents. Integration with other systems. In addition to train control, the signaling system interfaces with other critical components of the metro, platform screen doors, PS-DIS. In many modern systems, PS-DIS are synchronized with signaling to open only when a train is correctly positioned. Passenger Information Systems (PIS). Real-time data from signaling is used to update station displays, announcements, and mobile apps, keeping passengers informed about train arrivals and system status. Energy management and efficiency. By regulating train speeds and reducing stop-start cycles, signaling systems contribute to energy conservation and optimal track usage. Narrator wrap-up for section. Signaling and train control systems are the unseen yet indispensable guardians of metro safety and performance. Their advanced technology and robust design not only enhance operational efficiency, but also ensure that every journey is as safe as it is swift. As metro networks expand, these intelligent systems will continue to evolve, further pushing the boundaries of urban transit efficiency. 8. Testing, trial runs, and commissioning 1730 to 1930. Narrator. Once the construction, installation, and integration of all systems are complete, the project enters the critical phase of testing, trial runs, and commissioning. This stage ensures that every component from the tunnel and tracks to the signaling systems and electrical installations functions safely and seamlessly before the metro is opened for public use. Let's explore how these rigorous tests and inspections are performed to guarantee top-notch performance and safety. Pre-commissioning checks. Before any trial runs begin, engineers conduct extensive pre-commissioning checks. This involves verifying that all installations meet the design specifications and regulatory requirements. These checks include structural integrity. Engineers inspect tunnel linings, station boxes, and track alignments to confirm that all concrete, steel reinforcements, and joints are intact. Non-destructive testing methods such as ultrasonic testing or radiography are sometimes applied to detect hidden flaws. System integration. All individual subsystems, power supply, signaling, communication, fire safety, and ventilation are integrated and tested as a unified whole. This integration check ensures that data flows smoothly between systems and that control centers can command and monitor all elements efficiently. Safety audits. A comprehensive safety audit is undertaken covering everything from emergency evacuation routes and fire suppression systems to the reliability of backup power supplies. Regulatory bodies also review the results to ensure compliance with local and international safety standards. Static testing. During the initial phase of testing, static checks are performed where systems are activated individually. Component testing. Each component, such as track circuits, switchgear, interlocking systems, and communication devices, is tested under no-load conditions. Engineers simulate power supply, monitor signal integrity, and validate the operational status of all control panels. Infrastructure verification. Items such as escalators, lifts, platform screen doors, and ventilation shafts are activated to confirm that they operate smoothly and meet performance benchmarks. Static load tests and endurance tests are conducted to simulate prolonged usage. Dynamic testing trial runs. With all components verified individually, the focus shifts to dynamic testing, where operational scenarios are simulated. This phase is crucial because it mimics real-life conditions. Empty running tests. Metro trains are dispatched on the completed tracks in a controlled environment without passengers. During these tests, the train's dynamic behavior, such as acceleration, braking, and the interaction with signaling systems, is recorded. Special attention is given to how trains decelerate when approaching stations and how they perform in curves and gradients. System coordination checks. The interplay between the communication-based train control (CBTC) systems, automatic train operation, TO features, and emergency override functions are rigorously scrutinized. Engineers simulate various scenarios, including sudden stoppages, fault conditions, and simulated communication failures to ensure the system reacts safely. Full-scale integration trials. These trials incorporate all aspects of the Metro's operation in a series of repeated runs. This phase verifies that all subsystems track, power, signaling, and station operations work in complete harmony. Engineers monitor train performance, adjust system parameters, and troubleshoot issues in real time. Environmental and emergency drills. Part of the commissioning process includes preparing for unexpected events and ensuring the safety of both passengers and staff. Fire and smoke drills. Fire suppression systems, smoke extraction, and emergency lighting are activated to simulate a fire emergency. Evacuation protocols are tested to ensure quick and efficient passenger flow towards safe exit points. Power failure simulations. Backup systems, including system performance and fine-tuning. After extensive trials, data from all tests are analyzed to fine-tune system settings. This fine-tuning may involve adjusting train speeds, recalibrating sensors, or modifying software parameters within the signaling system. Engineers ensure that vibration, noise levels, and wear and tear are within acceptable limits to optimize long-term performance and passenger comfort. Final approval and handover. Once all tests are successfully completed, the project undergoes a final evaluation by a committee of engineers, safety inspectors, and regulatory authorities. Only after receiving a full certification that meets all operational and safety criteria is the Metro commissioned for public use. Narrator wrap-up for section. Testing and commissioning are the final gates to opening a Metro system. This exhaustive process guarantees that every element, from silent tunnels to high-speed trains, performs flawlessly under all conditions. It's a meticulous blend of engineering, technology, and safety, a final promise that every journey in your new Metro is as secure and efficient as it is impressive. 9. Benefits of underground Metro construction, 1930 to 2130. Narrator. While the technical complexity of an underground metro is astounding, its true value lies in the transformative benefits it brings to urban environments. In this section, we explore how underground metros not only ease transportation challenges, but also contribute significantly to sustainable urban development, economic growth, and enhanced quality of life. Alleviating surface congestion. One of the most immediate benefits of constructing an underground metro is its profound impact on surface transportation. By shifting a substantial volume of commuter traffic below ground, cities experience reduced road congestion. With fewer private vehicles clogging the streets, traffic flow improves, resulting in shorter journey times and decreased stress for motorists. Lowered emissions. Fewer cars on the road lead to a reduction in exhaust emissions, contributing to cleaner air and a lower urban carbon footprint. Enhanced safety. Reduced surface congestion means fewer traffic accidents and safer streets for pedestrians and cyclists. environmental impact, and sustainability. Underground metros serve as a cornerstone in modern sustainable transport strategies. Their benefits include energy efficiency. Compared to road vehicles, metros are far more energy efficient, particularly when paired with modern electrification systems that allow for regenerative braking. This process recaptures energy, reducing overall power consumption. Noise and vibration reduction. Underground systems significantly minimize noise pollution on the city surface, leading to a more peaceful urban environment and reduced acoustic disturbances. Preservation of urban aesthetics. By relegating the bulk of transit infrastructure underground, cities maintain their historical and architectural skyline without the intrusive presence of elevated railways or excessive surface bus lanes. Resilience to climate change. Underground metros are designed to be resilient. With proper waterproofing, ventilation, and emergency evacuation systems, these transport systems continue to perform reliably even under adverse weather conditions or extreme events. Economic and social advantages. Investing in an underground metro isn't solely about improving transportation, it has deep economic and social repercussions. Boosting urban economy. Effective metro systems stimulate economic activity by enhancing connectivity between business districts, industrial areas, and residential zones. They attract investments and support higher real estate values in well-connected neighborhoods. Job creation and skill development. The complex nature of constructing and operating metro systems generates substantial employment across multiple sectors from construction and engineering to operations and maintenance. Moreover, metro projects foster higher education and training opportunities in cutting-edge technologies. Inclusive urban mobility. Metros increase accessibility for all city dwellers by providing affordable and reliable transportation. This inclusivity bridges the gap between various socioeconomic groups, ensuring equitable access to work, education, and services. Cultural and social integration. The design of metro stations often becomes a canvas for public art and cultural expression, turning transit spaces into vibrant community hubs. Effective public transport fosters social interaction and promotes community engagement. Long-term urban planning and resilience. The strategic integration of underground metros plays a vital role in forward-thinking urban planning. Efficient land use. By moving transit corridors underground, cities free up valuable surface space for parks, commercial activities, and community spaces, thereby enhancing urban livability. Future-proof infrastructure. Underground metros are inherently adaptable. With scalable design and robust engineering principles, these systems can be integrated with evolving technologies such as smart monitoring systems and even future autonomous operations. Disaster preparedness. Modern underground metro systems are equipped with cutting-edge safety features, including fire suppression systems, emergency communication networks, and redundant power supplies. These features ensure that the metro remains a safe haven even during unforeseen disasters. Narrator wrap up for section. Beyond the impressive engineering feats, the real promise of an underground metro lies in its ability to shape a better future for our cities. By reducing congestion, lowering emissions, and catalyzing economic growth, underground metros stand as a testament to how innovative infrastructure can elevate the quality of urban life. They are not just transport solutions, they're a blueprint for a resilient. When it will run to crossing big and deeper river, what type of construction applied? When an underground metro line needs to cross a large, deep river, specialized construction techniques are employed to ensure structural safety and operational continuity. One of the most proven and widely used methods for such challenging conditions is the immersed tube tunnel (ITT) construction. This technique involves prefabricating tunnel segments in a controlled facility, transporting them to the site, and then installing them underwater, ensuring a continuous, watertight structure across the waterway. The process begins with extensive site investigations, including geotechnical surveys and hydrological studies, to determine the optimal alignment and understand the riverbed conditions. Once the site is prepared by dredging a trench along the riverbed, the precast concrete tunnel segments are floated into position using specialized barges. These segments are designed with robust, watertight joints and are carefully lowered into the trench, where they are interconnected to form a continuous tunnel. The ITT method is favored because it minimizes disruption to the river environment and offers excellent control over the quality and durability of the structure. After the segments are aligned and joined, the trench is backfilled with suitable material to secure the tunnel and provide additional resistance to hydraulic forces. Secondary waterproofing layers and grouting are applied to reinforce the integrity of the structure, protecting it from water ingress and the constant pressure exerted by the river. In scenarios where the river is extremely deep or where the geotechnical conditions are too complex for the ITT method, an alternative approach using tunnel boring machines (TBM) may be considered. However, for many big and deep river crossings, the immersed tube tunnel remains the most economical and efficient solution, offering a proven blend of reliability and adaptability in challenging underwater environments. 10. Conclusion: future trends. As we near the end of our journey into the depths of underground metro construction, let's take a moment to reflect on the engineering marvels we've explored and consider what the future holds for urban transit. In this concluding section, we'll summarize the core principles, highlight emerging trends, and share our final thoughts that underscore the transformative impact of underground metro systems. Recap of key phases. Throughout this video, we have dissected each critical phase from planning and route design to tunneling, station construction, track laying, power and signaling integration, and finally, rigorous testing and commissioning. Each phase is a vital piece of a larger puzzle that culminates in a safe, efficient, and reliable metro network that not only moves millions, but also shapes the urban landscape. Project planning and feasibility, where data, sustainability assessments, and financial strategies set the stage. Route design and geometric alignment, the careful art of creating a seamless underground pathway. Tunnel design and boring methods, showcasing technological innovations in safely carving through the earth. Station construction, transforming underground spaces into accessible, life-integrated hubs. Track laying, power, and signaling systems, the final arteries and nervous system that keep the metro operational. Testing and commissioning, the rigorous quality checks that ensure every train run is safe and smooth. Emerging trends in metro construction. Looking to the future, several exciting trends promise to further revolutionize the way we build and operate underground metros. Smart infrastructure. With the advent of the Internet of Things (IoT) and big data analytics, future metros will leverage real-time monitoring of structural health, energy usage, and crowd management. Embedded sensors can detect anomalies, enabling predictive maintenance and further enhancing safety. Green and sustainable designs. As cities pledge to reduce carbon footprints, there is an increasing emphasis on incorporating renewable energy sources, such as solar panels at station roofs and innovative water recycling systems within metro facilities. Advanced ventilation systems will not only improve air quality but also optimize energy consumption. Automation and digital transformation. Advances in artificial intelligence and automation will further integrate into the operation of metro systems. From fully automated trains with enhanced CBTC to digital twin simulations during the design and operational stages, these developments are set to elevate efficiency and minimize human error. Modular construction and rapid deployment. With an increased focus on minimizing construction time and disruptions, modular construction techniques are gaining traction. These approaches involve prefabricated components that can be assembled rapidly on site, ensuring quicker turnaround times while maintaining high quality and safety standards. enhanced passenger experience. Future metros will also focus on elevating the rider experience. With integrated digital information systems, immersive station environments, and enhanced security protocols, tomorrow's metros are designed to be not only efficient transit systems, but also vibrant public spaces. In conclusion, the underground metro stands as a testament to human ingenuity, a fusion of advanced engineering, technology, and visionary urban planning. As our cities continue to grow, the role of these subterranean transit networks will only become more critical. They reduce surface congestion, promote sustainable development, and act as lifelines that connect communities while shaping the future of urban mobility. Thank you for joining us on this in-depth exploration of underground metro construction and modern utilities. If you enjoyed this guide, please like, comment, and subscribe to Civil Engineering Edge for more detailed insights into the world of engineering. Let us know your thoughts, questions, and ideas for future topics in the comments below. Together, let's build a smarter, more sustainable urban future. Stay curious, stay inspired, and see you in the next video.